Hello, welcome to 13 Universal Learning Beyond Borders, and today we are still solving biology A-level questions on enzymes series 3. So all the questions are from past questions of Cambridge A-level, and I am Shedro. So let's go to the first question, guys. Says ethyl glycol. You can see that. Can you see? Ethyl glycol is a chemical used to prevent water from freezing. Okay. Now, if ethylene glycol is swallowed accidentally, it is metabolized by an enzyme found in liver cells to produce a toxic product. Okay. So it is metabolized. All right. So the enzyme normally catalyzes the oxidation of ethanol to a harmless product. All right. That is that enzyme. And we have people who have swallowed ethylene glycol are treated with large doses of ethanol. Okay, this prevents formation of a toxic product, can see that, and allows the body to excrete ethylene glycol. So let's go. So which statement describes why this treatment works? Number one, ethanol binds near the active site on the enzyme, altering its shape. So let's look at the options. So please, if you check this question very well, the ethylene glycol is a chemical used to prevent water from freezing. The if ethylene glycol is swallowed accidentally, it is metabolized by an enzyme found in liver cells, okay, to produce a toxic product. Then I said the enzyme normally catalyzes the oxidation of ethanol, okay, to a harmless product. So this is the substrate of this enzyme. This actual substrate is ethanol, right? That is the enzyme that metabolizes ethylene glycol, right, to a toxic product. Okay. Then I said people who have swallowed ethylene glycol are treated with large doses of ethanol. Okay. Now ethanol can bind to this enzyme and ethylene glycol can bind to it. However, you see, ethylene glycol, when it is metabolized by the enzyme, it forms a toxic product. Okay. But when it is metabolized by ethanol, it forms a harmless. So both of them can be metabolized by this enzyme. All right. So this they say this prevents formation of toxic and allows the body to excrete it. So it seems to me, before we go into the question, that ethanol and ethylene glycol bind to the same active site of the enzyme found in the liver. So both of them have complementary shape to the active site of this um, particular enzyme, that is ethanol and ethylene glycol. And this, you see, remember what is said here, that glycol treated with large doses of ethanol. All right, when people swallow ethylene glycol, then they are treated with large doses. So by increasing substrate concentration, you can reverse the effect of this enzyme on ethylene glycol, because it works on it to produce a toxic product. So we know that most likely that there's a which statement describes. So we're dealing with competitive inhibitor here. Okay, how do I know? They bind to the same enzyme and they bind to the active site. How do I know? The enzyme metabolizes them. Let's go to the questions. A says ethanol binds near the active site. Near the active site on the enzyme alternate shape is talking about non-competitive. B says ethanol binds permanently to the active site. It does not bind permanently, all right, because that is why we can still because it's converted to product. Ethanol converted to a harmless product. So ethanol is converted to harmless product. Okay. Now, so B is wrong. C says ethanol changes the tertiary structure of the ethylene enzyme. Okay, it does not change it. It doesn't denature it. Okay, doesn't alter it. It's just a normal substrate that is converted to a product. There's no clue to that. But look at the ethanol is more likely to bind to the active site. Yes, it's more likely to bind to the active site of the enzyme. Okay, what do you think is the answer? What do you think? I think is D. This right. Hey, are you here? Are you here? Right, let's go on. Let's go to this next question. So, which words from the table complete the paragraph about enzymes? So, when the pH of an enzyme, all right, pH of an environment is decreased below an enzyme's optimum pH. We have one bond between. Okay, look at it. So you see that I said in the former video, I think series 2, okay, change in pH will always break two bonds, hydrogen and ionic bonds, and these bonds are formed between adjacent R groups. Okay, so and hydrogen bonds and let's see, and ionic bonds, they also help to form tertiary structure. All right, yeah, they form tertiary structure. So look at it. All right, I don't want to waste time here, but guys, you know what we're talking about. If this is an enzyme, look, this is a an let me use another thing here. You have this is what is it called, amino acid, okay, forming peptide bond with another amino acid. Okay, each of them have an R group. Yes, so the interaction between an R group, this R group, and that is another R group here, you know that. Okay, let me call this R group 2. So these R groups can form hydrogen bonds, or they can form um, ionic bonds. Okay, so if there's an attraction bond between ionized carboxyl group and ionized amine group, that is ionic bond between the hydrogen of an NH group and oxygen of a CO group, that is hydrogen bond. Okay, so if you look at the option, hydrogen and ionic, yes, it's between the arrow group, yes, the tertiary structure. So A is the answer. Okay, it's not only the hydrogen, right? Ionic is also bonds formed between adjacent that is affected by change in pH. Okay, because it's not secondary, because ionic is not part of secondary. Peptide is not affected by pH. Peptide is not affected by pH. So the answer is A. Okay. Okay, guys. Now look at this question. You can try it, pause the video and try it once I finish reading it. The lipase is a digestive enzyme produced by the pancreas that catalyzes the hydrolysis of dietary lipids. The table shows how the pH of a liquid food containing a high proportion of lipid decreases over time. So you can see that. So guys, look at this. So look at, this is time, this is pH of liquid. So can you see with time the pH is decreasing. All right, why is the pH decreasing? Have you thought about that? Why is the pH decreasing? Why? Tell me, why do you think it's decreasing? They say, which statements are possible? Explanations of the results of the experiment between 50 and 60 minutes. So this is 50 to 60 minutes. Can you see that the pH remains constant? Something has happened here. So we're looking for explanation for that. These are the possible explanation. So which one, okay, are you going for? All right, let's crack it. But guys, remember that lipase breaks down lipids. It breaks down lipids, triglycerides to fatty acid and glycerol. So fatty acid lowers the pH, right? But when you come here, you see that the pH remains constant. Why? Okay, so one says enzyme concentration becomes limiting factor. Enzyme concentration is not limiting factor, because once enzyme lipase breaks down the lipid to glycerol and fatty acid, it releases them, binds to another one. Enzyme remains concentration remains unchanged, so it cannot be a limiting factor. Solvent concentration becomes limiting factor. Yes, it's possible that all the lipid has been broken down. Okay, so this remains constant, so 2 should be there. 3 says all enzymes active sites are saturated. No, we are not increasing the substrate concentration. All right, if we're increasing the substrate concentration, you can say that all enzyme active sites are saturated, but we added a fixed concentration of the substrate. Okay, so this is not correct. 4 says denaturation of the enzyme byproduct. Yes, because there's a change in pH. Change in pH breaks hydrogen bonds and ionic bonds and could disrupt the tertiary structure of the active site. So 4 is right. 5 says the product are acting as competing inhibitors. Yes, it's possible that the product binds to lipase enzyme because of accumulation of product. It that's what is called end product inhibition. Okay, that may be what is happening here. So see 2 is correct. Okay, I think 4 is correct and 5 is correct. So which option does that show? That is D. Next question. The AIDS virus produces long polypeptide that is hydrolyzed by a protease enzyme, producing several smaller. So a protease enzyme hydrolyzes it and produces several smaller polypeptides. This virus protease is a target, so it's an enzyme, so it's a target of anti-AIDS drugs. Now I want to say this, that most drugs, all right, most drugs act as inhibitors of a particular enzyme, right? So there's a which feature is essential, look at it, for the success of these drugs. All right, is okay, look at A. Okay, just pause it and then check on it. A says a complex structure that inhibits many types of virus enzyme, many types. Now, this is just one enzyme, virus protease. Okay, just one, right? Look at this. A molecule contains a heavy metal atom that is non-competitive. Non-competitive inhibitors of enzymes. A molecule contain a heavy metal atom that is a non-competitive. So this is a anti-AIDS drugs. Okay, like that doesn't actually explain this, all right, because they didn't give us any target whether it is non-competitive or competitive, right? No information on that. All right, there's a protein that can act as a competitive inhibitor on protease enzyme. We were not given any clue about the type of competitive inhibitor. This says a specific structure that inhibits only viral proteins. Yes, that's specificity. That's what we found out. Okay, so this viral is the target for anti. So because if it inhibits only viral proteins, that is okay. But if it inhibits other human enzymes, it will cause a lot of side effects. Please, it should inhibit only viral proteins and kill off the virus of our body. We don't like viruses; they're bad, too bad. Okay, so the answer is D. Yeah, let's go to number 5. A quality of an enzyme was added to a quantity of its substrate. The graph shows the changes in concentration of the enzyme. The substrate, the enzyme substrate. Okay, let's look at over time. All right, look at it. All right, there's a which graph shows the changes in the concentration of enzyme substrate complex. Now, if you look at this, this is the concentration of the product. As time continues, product is formed. Remember that during reaction, product is formed. The amount of product increases with time and remains constant. Okay. Now, substrate is used up. This explains substrate. So as reaction goes, substrate is converted to product. So the amount of substrate decreases over time. So it cannot be this. Neither can it be this. This shows the concentration of enzyme. Enzyme concentration remains the same. They remain unchanged. All right. It doesn't increase, it doesn't decrease. Enzymes are not used up in reactions. Okay, look at this. So the most likely answer is this. So at the beginning of the reaction, ES complex is formed and they dissociate to form product. So they build up at the beginning, and then by the time they start dissociating, because temporal bond is formed between enzyme and substrate, those bonds break or convert the substrate into product. So as ES complex is being converted into product, their concentration will decrease. Okay, so the answer is what? A. Alright, so which is correct for a competitive inhibitor of an enzyme? Yeah, which is correct, guys? So inhibitors binds to a site on the enzyme other than no competitive inhibitors, guys. I've said it before. They are they bind to the same site, okay, the active site of the enzyme. In previous video I drew something like this. So if this is the enzyme, I'm drawing the enzyme. Okay, this is the active site I'm drawing. Okay, so if this is the substrate, okay, the substrate should have complementary shape to the enzyme, and let's assume that this is the inhibitor is similar to the this is substrate, this is inhibitor I. Okay, yes, this is enzyme that's Mr. Can you see, guys? Don't forget this, please. Look at it. The enzyme has this active site of the enzyme. Okay, the active site is complementary to both substrate and inhibitor. So both substrate and inhibitor, they are similar. So this is competitive. So when this substrate binds, it competes for the active site, all right, or the substrate. So when it binds, it blocks the substrate, right? So A cannot be the answer. It doesn't bind to alloxylate site. Inhibitor binds on the active site, yes. And if you increase substrate concentration, it decreases the effect on the level of, okay, inhibition. Yes, increasing it. I think we did it the other time. If you draw a graph, watch this. Remember this graph? This is a graph of substrate concentration against rate of reaction. So the reaction with that inhibitor, you remember, it goes up levels. With competitive, it's going to catch up with it. Watch, as long as you keep increasing substrate concentration here, okay, so it reverses the effect of the inhibitor. That means we still reach the same Vmax, all right, Vmax, okay, the same maximum, okay. But if it is non-competitive, it will lower Vmax, okay. So that B makes sense, all right. I think is the answer, because if you check C, inhibitor binds to the active site, the substrate concentration has no effect. No, if it is competitive, substrate increases substrate concentration has effect, all right. Inhibitor binds it, so the answer is B, all right. Okay, it's B. So 7 says, which statement about the effect of all enzyme inhibitors are correct? All enzyme change the shape of the active site? No, it is only competing inhibitors that change the shape of active site. All right, the nature of the enzyme, not all of them. The nature of the enzyme. 3 says reduce the rate of enzyme catalyzed reaction. Yeah, all of them reduce it. All of them. So the answer is what? D. All of them do this. Not all of them. The nature of the enzyme. Not all of them change shape. Not competitive change, or competitive does not change shape. Active site binds to it. Okay. So please check up on us. We want to hear your feedbacks. All right, please ask questions, share the video, like it. Now, it says the graph shows the rate of reaction of an enzyme reaction. Which graph shows the effect of increasing the concentration of the substrate at two different concentration of competing inhibitors? See that thing was said. Please tell me the answer. What do you think is the answer? Is it, no, is it this? No, it's going to catch up. A cannot be the answer. B looks at the answer, because this is competitive. This is no inhibitor. This is, okay, non-competitive, right? It's going to catch up. So look at this. This cannot be this. It cannot be this. It's only B, because competitive will get to the Vmax. All right. So B is the answer. Which levels of protein structure are always involved when competitive and non-competitive inhibitors bind to enzymes? Interesting, guys. Watch this. This is interesting. Do you want to try this? Yeah, try this. So watch this. If this were to be an enzyme, let me change style. Okay, this is like this. Okay, sometimes an enzyme has, okay, it has something like this. Okay, the shape can be like this. It has more than one tertiary structure. So do you see it has, this is a binding site, this is the active site. There's another site other than active site. This is called allosteric site, this part. But this is active site. This is allosteric. That is active, that's allosteric. So non-competing inhibitors bind to allosteric and change the shape. Competing inhibitors bind to the active site and blocks the substrate. Okay, so they are all tertiary structure. Okay, they are tertiary structure because they are 3D shape. They're not secondary, they're not quaternary, just tertiary structure. So the answer is D. Okay, All right, which statements are true about the optimum temperature of all enzymes? Yeah, that's interesting. It is the temperature at which enzymes work best. Fantastically correct, guys. Yeah, enzymes works best at optimum temperature. Two said it is the highest temperature at which enzyme will work. No, it's not the highest temperature. The highest temperature made the nature of the enzyme to break hydrogen bonds and distort the active site, make it less complementary. Okay, it's not the highest. Optimum is not the highest. Okay, so it is the best that no, not enzyme. Okay, so it's the best between 35. All so enzymes have different optimum temperature. Okay. So I think, what do you think is the answer? What do you think? I think, what do you think? Number one, C only. I go for number one. Okay, guys, it's been amazing with you hanging out. Thank you so much. Please leave your questions, comment, like our videos. Okay, so I'm gonna be going for series 4. Thank you for joining us with Enzymes series 3. Remember, I'm Shedro. See you next series. Thank you. Bye.